Welcome to a lesson with Dr. Powell. In this video, we will look at a couple practice problems that deal with verifying an M delta definition of a limit that it holds, or epsilon n definition, okay, of it holding. So let's take a look at these two practice problems. Now to make it a practice problem, I invite the viewer to pause it and try it on your own, and then when you're ready, come back and look at the solution. All right, on your mark, get set, pause. All right, now here we go. Okay, so let's take a look. We'll take a look at this and look at the solution for this one. We have notice that we're coming on the right side, and the y values, we want them to be heading off to negative infinity. So when we say at the beginning, normally we say something like given epsilon greater than 0. Well, what does that represent? That represents the y closeness, if you will, to where we're heading toward. But how do you get close to negative infinity? I mean, how do you represent that? Well, you can represent that by saying, given any location, I'm going to be under that, or another location could be less than it, and so forth. So pretty much the y closeness is simply just going to be a position, and we're going to be saying given any position, no matter how low it is. So with epsilon greater than, with epsilons, we're like any distance, even small distance away from a point. Here we're going to say any position, and including any position no matter how negative or low it is on the y-axis in position. So let's take a look at that. And we're going to say, and what we use instead of epsilon, we let m be the position, like y equals m. So given m, and I'll just say that, given m could be any other number line, it could even be way up positive, but really the crux of the matter is, this will work no matter how low the m gets. So that's what's important. Down toward negative infinity, or in that direction at least, that is. So given m, the normal statement says there exists a delta such that, what we're going to be doing is we're going to be finding the delta. Let delta be, because we want to verify the statement. Let delta be equal to something, that shows that such a delta will exist, because really the statement has there exists a delta such that, but we're going to be looking for that. So that's why we're going to just say let delta be equal to something. Then if some inequality is holding with delta, then we're going to have something else. So let's take a look at that in a picture. So this is a transformation of 1 over x, a nice one, right? But it's going to be, if you're thinking about it, we've taken 1 over x and we've shifted it to the right one, and then we've reflected it. So it's going to look something like this. The right one would be like this asymptote. Instead of x equals 0, it'll be x equals 1. But then things are going to be flipped. So it's going to look like this coming down, and then the other side coming like this. I mean, you could kind of plug in some values or investigate to see kind of that's what's going to be happening. Or even just realizing if you plug in 1 plus into that, minus, what's 1 plus? Minus 1, that's going to be like a 0 plus. It's going to be like a negative 1 over 0 plus. This part, this part right here is positive infinity, with the negative would be negative infinity. So, kind of thinking about it that way, yeah, we can see that the y values on the right side as we head will go to negative infinity. In fact, you can even just see that by just looking at this limit statement, just assuming it's true, right? So as the x values head to 1 from the right, these guys will be going down. Okay, so enough for that. We just getting a picture so we can look at it. Okay, so given m, what is that going to look like? Just kind of get any position. Think of it as getting lower. So given some y equals m, there's going to be a delta value just on the right side, such that if we are in between, if we're just delta away from 1, then the function is going to be what? In here, right? Getting close downward to negative infinity. Basically, it's going to be the value of the function itself. The y value coming out of the function is going to be less than m. So then f of x will be less than m. So what's this condition right here? That's simply saying that the x value is delta this way of 1. So, so if we have any x value in here, some x value in here, x minus 1, because x is going to be to the right of 1, that's going to be positive, and we want it to, it'll represent a distance to the right of 1, and we want that distance to be less than delta, but we're also excluding the case when x is actually equal to 1. It's an asymptote anyway, so like that. Okay, so no absolute values because we're just thinking about x as being on one side of 1. So that's the statement there that we want. So 0, x minus 1 less than delta. All right, so we got to find the delta that would work. In the picture, you can see a delta that would work. In fact, maybe to make this a little bit more clear for us, let's redraw this a little bit. Okay, so let's think, just so we can have some more space in the picture. It's coming through, it's going like this down, it hits this at some point, right? All right, so the distance from here to here is the delta that we're after. The point of exit entry is enough. So if x is that much from delta, then of course the y value of the function is going to be lower than this line y equals n, right? You can see that in the picture, the way it's drawn, and knowing what this graph looks like knowing what the function is algebraically, what the graph looks like. They're equivalent in many ways. So if we take a look at this and think, all right, so we just need to know that entry, right? That point of entry. Now we know the y value of this, or entry, exit, whatever you want to think about on this line for this region down here. So the y value here is equal to m. You know the x value right here at this position, let's get the x value right there, that would be x is equal to 1 plus delta. So 1 plus delta is the x value. So the y value can be found just by knowing it's m or by plugging in 1 plus delta, and that's the key. F of 1 plus delta will be equal to m. So this is how we can find the relationship between delta and m. So we can write what delta is in terms of the situation, which is dependent upon m. So delta will be written in terms of m. Okay, so in order to do that, right here we know what f is. F is negative 1 over x minus 1, and we set that equal, and but we want to replace our x with what it is, which is 1 plus delta. So 1 plus delta is x. Okay, so when we plug 1 plus delta in, so using this, we want that to be equal to m. Basically, we just wrote down this equation right here with what f was. All right, so this gives us a relationship between delta and m. We just need to solve for delta. All right, so we can multiply both sides by a negative and reciprocate both sides if you like just take a reciprocal of both sides, which is great. I mean, if two numbers are the same, their reciprocals will be the same. It's kind of a nifty idea. We just raise both sides to the negative 1 power, same idea. So, but before I do that, I multiply both sides by negative, so I have a negative m. So reciprocal of negative m is negative 1 over m, and that's going to be equal to this guy down here. Now notice right here, the 1 and the negative 1 cancel, because we can remove the parentheses right there freely, and we end up just simply getting delta. Oh, awesome. Okay, why? Because we took a reciprocal where this was positive, that's negative, and taking the reciprocal, we end up just getting the denominator is what comes up to the top over positive 1 is just itself, which is just delta. So delta is equal to negative 1 over m, and that's what we need, and that's enough. We just verified that such a delta exists by saying what it was in terms of m in the situation by looking at the picture and the description of what the function is, and giving an explicit relationship between delta and m. Okay, the next practice problem will actually be in the next video, so stay tuned. Thanks for watching.